For the chi-square test of either variance or standard deviation, the critical value method is the classical method, is the one that we use a lot of the time because the calculator is not available to us. And when the calculator isn't available to us, the chi-square table method is the only one we can do by hand. But if we're given computer output, then we can actually do the p-value approach. And so that's what we're going to do. But there's something else to consider here. When we do the p-value approach, we're going to have to watch out for a two-tailed test, which is the example I'm going to be going through right now, because you're going to see that you're going to have to choose whether your chi-0 squared is on the left or the right, depending on what the value is and the chi-square table. So it's not that hard, but it's just a little tricky at first. So one important attribute of a storage device for electricity, i.e. a battery, is the variability in storage capacity. So consistent capacity is desirable so that consumers can accurately predict the amount of time they can expect the battery system to last under normal conditions. So you can imagine there are companies that are working on cell phone batteries. They want them to last a consistent amount, or the companies that buy those batteries want them to last a consistent amount. So Genesis technology engineers have determined that one particular storage design will yield an average of 88 minutes per cell with a standard deviation of 6 minutes. During the past few weeks, the engineers have made modifications to the design and are interested in determining whether this change has impacted the standard deviation either up or down. Ooh, either up or down. Interesting. So that sounds to me like it's going to be a two-tailed test. And when we look over here, with the computer output, which I've already highlighted with a few different colors, you can see in the purple box up here that indeed it is a two-tailed test. Standard deviation up or down, meaning two-tailed, could go either direction. All right, so what type of test was this? Well, this was not a right-tailed test. This was a two-tailed test. Very important. Two-tailed test because it's a not equal to test. Now the parameter being tested is the standard deviation. It's sigma. It says right there, little sigma. Now how would we write this if it was going to be variance? Well, you'd write it with sigma squared instead of sigma. And 6 squared is 36. So it would be sigma squared equals 36 or sigma squared not equal to 36. And that's it. Same idea, just with sigma squareds instead of sigmas. Some computer programs will do standard deviation. Some computer programs will do variance. But other than that, it doesn't make any difference. Now, how many storage cells were sampled? And what was the variance? All right, storage cells sampled. You can see it would be right here in this little blue box, but I took that blue box away from you. And that means you're going to have to use the degrees of freedom. So the degrees of freedom is 11. And that means that your sample size is 12, right there. And then I'm going to give it a little box just to match the box that we had from our table. There we go, from our output. So it's in the blue information, right? And it wasn't given directly to us. We had to calculate it, but luckily for us, that's one of the easiest calculations we ever do. Now the variance of the sample. The variance of the sample is given to us right there. It's 26.6. So that would be our S squared. And I gave it kind of an orangish highlight so it could match the output highlight I have up here. But I blocked off the standard deviation because I'm mean like that. It's left blank. So that means we're going to have to calculate it right here. All right, well, remember that the standard deviation is just S, and we already know what S squared is. So we're going to have to take the square root of that. There we go. So just remember, S is the square root of S squared. Right? We learned that from an algebra class a long time ago. And that means that our S is going to be approximately the square root of 26.6. So I'm going to go grab a calculator. Second square root, it's above the x squared button, 26.6. And I get 5.175 or 1575. And of course, everything's approximate because all of this was rounded anyway. Now, I left a little blank in here, and it's because I wanted to remind ourselves that these have units. It's been a long time since we've seen them. This particular data set was talking about minutes, the minutes right here. See that right there? In minutes. So that means that our unit for our S is actually minutes. And just a little reminder, because it's been a while, this is actually minutes squared for the standard deviation, right? Because variance, for the variance, because the variance has the unit squared, which of course is kind of worthless to us for interpretation values, but nevertheless, that is the unit involved. So it's minutes squared. All right, so now we're going to go to the infamous step 4. This is the part that's a little bit harder for us in a p-value method than it is in a classical method. Not normally, but for chi-square ones it is. Now here's the trick. We need to figure out where our test statistic is. Our test statistic was given to us as, I gotta go back up here. It's right there in the little red box. It's 8.13, right there. Now the trick is, we know that it's 8.13. We remember that we had degrees of freedom 11. And the question is the 8.13 over here on the left, or is it over here on the right? Okay, so what we need to do is we need to go to the chi-square table and look at that row, right? So go to chi-square table, look at the row, and see if 8.13 is on the left side or on the right side, or where we think it would be. So I need to go back up to that table. Here we are. And I want to look at this row right here, the 11 row, right there. And I want to see, okay, 8. 8 is kind of a big number, but where would it fall? Is it over here on the right side with 17, or is it closer to the left side with 5? You can just kind of do a subtraction in your head. 8 take away 5 is about 3 away. 17 take away 8 is about 9 away. That means that it's closer to this side. That means that the 8.13 is actually the number on the left side. So you're kind of looking at the table and that row for your degrees of freedom and trying to figure out, is the test statistic I found, is it more one of these numbers on the left of that bar down the center, or is it more one of these ones on the right? Since 8 is closer to 5, that means it's the one on the left. And don't forget that even though the graph is skewed right, that graph is still an x-axis on the bottom, or excuse me, that line is still an x-axis on the bottom. So that means that the number on the left is actually the 8.13. There, and I just labeled the graph as such. Now keep in mind, we don't actually get to know what the one on the right is. We don't have the information for that, and we're not going to figure it out. But we know that the left-hand value is 8.13. And there we have it. So I just wrote that up a little really quickly. So we looked at the DF equals 11, degrees of freedom equals 11 row of the chi-square table. We can see that 8.13 is closer to the left-hand values than the right-hand values. And so that's why we placed it on the left-hand side of the graph. Of course, it was closer to the right hand, you'd make it the right one. And you don't get to know what the other test statistic is. You only found one of them. That's all you're interested in. So you don't get to find out the other one. All right, so that's the only hard part, just kind of looking at that table and figuring out, hey, is this closer to the left or the right? Now that we know that, we still know our p-value, which labeled up at the top is p-value is 0.597. And that came right from the output right here. It says p-value is 0.597. So that means that we are going to not reject the null hypothesis, because one thing that hasn't changed is you only reject null hypothesis if your p-value is low, lower than your alpha. And your alpha here is 0.05, and 0.597 is nowhere near lower than that. There, and I just typed that up. No, this is not statistically significant because your p-value, which is 0.597, is not less than your alpha, which is 0.05. And so we do not reject the null hypothesis, and that means it's not statistically significant. And I have just a little recall in here. Recall that to reject H0 is statistically significant, and to not reject H0 is not statistically significant. All right, now what conclusion would we reach? Well, if we're not rejecting the null hypothesis, we would say there is not enough evidence to support the claim that, and then we'd have to go write up the claim. There's not enough evidence to support the claim that the modifications in the system affected the standard deviation either up or down from 6 minutes. All right. Now, if we're making an incorrect judgment here, what kind of error are we making? Well, let's see, we did not reject the null hypothesis, so that would be a type 2 error. Let me go back to that section of chapter 10. Remember here from 10.1, long time ago, that if you do not reject the null hypothesis, your only option is either that you're doing it correct or you're making a type 2 error, right? And that's the only option we have because we did not reject the null hypothesis. And there we have that. So type 2 error is the one where you did not reject the null hypothesis. So if you did this incorrectly, that would be the error you're making.